2024 was supposed to be SpaceX's year of triumph. Starship test flights dazzled, but NASA's engineers quietly flagged a critical issue: the Super Heavy booster's fuel transfer tube. During a routine static fire, Booster 14 exploded in a fireball at Starbase, confirming NASA's worst fears. The culprit? The very tube meant to deliver liquid oxygen for the rocket's landing maneuver. This wasn't just a setback, it threatened the entire Starship architecture and NASA's Artemis lunar ambitions. The investigation zeroed in intense engine vibrations and cryogenic temperatures had pushed the transfer tube past its limits. The flaw wasn't a simple fix, it was a fundamental design problem. SpaceX faced public scrutiny, while NASA's caution was vindicated, but both knew the Mars dream was at risk. The crisis forced an urgent, high-stakes collaboration between NASA and SpaceX. The only way forward, a revolution in rocket design. Investigators discovered microscopic stress fractures in the transfer tube's steel, tiny cracks invisible to standard inspections. Under the stress of launch and re-entry, these cracks grew, threatening catastrophic failure. For Mars missions where reliability is everything, this was a deal-breaker. Each flight became a game of Russian roulette. A single fracture could destroy the rocket mid-mission. NASA's safety culture, shaped by past tragedies, could never accept such unpredictable risk. The problem: no way to predict when the tube would fail, and no redundancy. The Mars program was on hold until SpaceX could engineer out this fatal flaw. The message was clear: redesign or risk losing the future of human spaceflight. SpaceX had to act, fast and fundamentally. The dream of Mars now hinged on solving a problem smaller than a human hair. Elon Musk and SpaceX didn't patch the problem, they scrapped the old design. The internal transfer tube was eliminated entirely, forcing a complete rethink of the booster's architecture. Every assumption was challenged. The team worked around the clock, exploring radical new configurations. The redesign wasn't just technical, it was cultural, demanding SpaceX abandon years of sunk costs. The fail fast, iterate fast philosophy was tested like never before. Musk led marathon sessions, pushing for a booster that was stronger, simpler, and safer. The new design rerouted liquid oxygen, removing the vulnerable tube and reshaping the entire vehicle. It was a gamble. Months of delays, enormous resources, but a shot at true reliability. Other companies might have settled for a patch. SpaceX chose reinvention. The result? A new generation of rocket, born from crisis. SpaceX was about to prove its agility on the grandest stage. Enter the Block 3 Super Heavy booster, a fundamentally new machine. The internal transfer tube was gone, replaced by a robust integrated propellant system. SpaceX developed new stainless steel alloys, stronger and more fracture-resistant at cryogenic temperatures. Advanced 3D printing allowed for seamless, lighter, and stronger components, reducing failure points. Active thermal management circulated cryogenic propellant to prevent dangerous hot and cold spots. The result? A safer, more efficient, and easier-to-build booster. Manufacturing was streamlined, keeping SpaceX's rapid production pace intact. Block 3 embodied a new philosophy. Materials, structure, and manufacturing all developed in concert. This was a rocket forged in failure, reborn stronger than ever. The Mars dream had a new foundation. Powering Block 3 is the Raptor 3 engine, a leap forward in performance and reliability. Simpler to manufacture with fewer parts and welds, it's designed for maximum reliability. Each engine delivers 350 tons of thrust, up from Raptor 2's 230, enabling heavier payloads and more ambitious missions. 33 engines generate over 11,500 tons of thrust, more than double Saturn V. Innovations include higher chamber pressures and advanced super alloys, pushing the limits of chemical propulsion. 3D printed components withstand extreme heat and pressure. The Raptor 3 is the most advanced rocket engine ever built. Its power makes the Block 3 architecture possible, keeping payload capacity high despite a heavier, safer booster. Developed in parallel with the new booster, it's the heart of SpaceX's Mars ambitions. With Raptor 3, SpaceX is years ahead of the competition. The Starship redesign highlighted the clash and synergy between NASA's caution and SpaceX's speed. NASA's culture, shaped by tragedy, demands exhaustive testing and peer review. SpaceX, in contrast, builds, flies, and learns, embracing failure as a path to progress. NASA's scrutiny caught the fatal flaw. SpaceX's agility delivered the solution in record time. The tension between these philosophies is the drama of modern spaceflight. NASA tempers SpaceX's risk-taking. SpaceX accelerates NASA's ambitions. The Block 3 redesign proved that together, they can solve problems neither could alone. NASA brings oversight and vision, SpaceX brings innovation and relentless drive. Their partnership is fraught but powerful, creating a new paradigm for exploration. The Mars program's survival depended on this unlikely alliance. When caution and speed combine, extraordinary things happen. The Block 3 redesign didn't just save a rocket, it saved the future of human space exploration. SpaceX turned a near-fatal flaw into a generational leap, pulling the Mars program back from the brink. While others are still developing next-gen rockets, SpaceX has already built, failed, and reinvented. Block 3 and Raptor 3 put SpaceX years ahead. No one else has a fully reusable system with this power. The implications are profound. The path to the Moon, Mars, and beyond now runs through Starship. The ability to launch over 100 tons to orbit and refuel in space changes everything. Progress is forged through failure and bold reinvention. The explosion that once symbolized crisis is now the catalyst for a revolution. The journey to Mars is long, but for the first time, the vehicle to get us there is ready.